Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I see all sorts of questions saved up. Let's see. Let's look at one sort of a physics question from Jimmy here. In quantum chromodynamics, they ask, what is color confinement? All right, we're going to dive into some particle physics. It was the field that I first got serious about studying when I was a kid. In fact, I even worked on QCD, quantum chromodynamics. So, okay, let's talk about what this is about. So, inside atoms, there are nuclei, there are electrons outside the nucleus. The nucleus is made of protons and neutrons. For a while, people used to refer to protons and neutrons as elementary particles, because it seemed like there was, you had a proton, you couldn't split it apart into anything else. But it was discovered in basically by the 1960s, sometime 1950s, 1960s, the protons they're certainly not just points, they have an extent. So a proton is about 10 to the minus 15 meters. That's a 1,000 trillionth of a meter across. They're about 100,000 times smaller than the whole atom is maybe like a hydrogen atom, which has a proton at the center and then an electron outside. The whole atom is about 100,000 times larger than the proton that's in the middle. So protons are pretty small compared to complete atoms. Most of an atom is kind of empty space, which is why when Rutherford originally discovered the atomic nucleus back in, 1910s or so, he did that by shooting other particles at atoms and found that most of the time, the other particles would just go straight through the atom because they were kind of going through the empty space in the atom. But just occasionally, they would hit the nucleus and then they would be deflected a long way. And that kind of pattern of doing experiments of you shoot something at an object and you see, does it just go straight through because there wasn't anything there, or does it hit some hard piece and bounce off in a very different direction? That's a sort of pattern of doing things that was repeated multiple times. So, okay, it became clear that protons were not point particles. So the question is, what are protons made of? And that wasn't clear, but then the most significant thing that happened, this was around 1970-ish, early 1970s, was people did the same kind of experiment that had been done with atoms by Rutherford when he discovered the atomic nucleus. They did the same kind of experiment on protons. And what they did was they shot electrons, high energy electrons, at protons. And they wanted to see, would the electrons just go straight through, or would the electrons hit something hard and be bounced in a very different direction? And what was found was that much of the time, the electrons would just go straight through, but occasionally the electrons would hit something and bounce in a very different direction. There's a phenomenon called deep inelastic scattering. And so the idea was that it's sort of inelastic because it doesn't just sort of, well, it's not quite the right word really, but that was what it was called. It doesn't just sort of bounce off. The reason it was called inelastic scattering had to do with thinking about whole protons hitting each other and sort of bouncing off as complete protons, as opposed to sort of shattering into pieces in some sense. But in any case, the thing that was discovered was you shoot high energy electrons at a proton. And by the way, one of the things that was being assumed there is that while protons are extended objects that have a definite size, electrons were thought at the time, are still thought by many people, not by me though, to be sort of point particles that don't have any extent. So they're a good sort of probe of, what's inside the proton. Oh, you shoot this thing that's basically a pure geometric point, doesn't have extent. You shoot it at the proton, you use that as a probe of what's inside a proton. So the big thing that was discovered was that there were, inside the proton, there were some kind of hard bits that would occasionally cause the electron to scatter in a very different direction. Those things were initially called partons by my friend Dick Feynman, actually. The things that are the parts of a proton. Okay, so it became clear there was substructure inside protons. It wasn't clear what it was. Okay, and another part of the whole sort of world of physics, there was this thing called the quark model, invented by another person I knew quite well, Murray Gell-Mann, along with another person, George Zweig, who I also have known for many years. But in any case, that was invented in 1962, maybe, and maybe 1960. Might be off by a year or two. But in any case, the idea, okay, so let's talk about the quark model. The question is, okay, first point is, protons were discovered as sort of what were originally thought of as elementary particles. Later on, neutrons were discovered. Both protons and neutrons are sort of known pieces of an atomic nucleus. It was a big question of how does the atomic nucleus, how is it stuck together, so to speak? Because all protons are positively charged particles with electric charge +1 in some units. And if you put together lots of like-charged things, they repel each other. So inside an atomic nucleus, you would think, oh, all these protons, which all have the same charge, they're all going to just repel each other and the atomic nucleus is going to fall apart. But that doesn't happen. And the reason it doesn't happen is because of this thing, it's called the strong nuclear force, that is a strong force that holds protons together, but it's a short-ranged force. So if you, for something like an electrical repulsion or attraction force, if you have two objects that are a distance r apart, then the force goes like 1/r². It's an inverse square law, same as the inverse square law of gravity for electrical kinds of things. But the strong nuclear force falls off much more rapidly than that. When you get beyond a distance of, well, pretty much around the size of a proton and atomic nucleus, they're sort of all comparable in size. If you get much beyond that distance, the strong nuclear force has fallen off in strength tremendously. So in the 1930s, it was realized sort of how do you account for the strong nuclear force? What actually is it? Well, one thing to say is when you think about electromagnetism, electromagnetic forces, force of electrical repulsion or magnetic kinds of phenomena, the way to think about what's going on there is you've got this charged particle, like an electron with an electric charge, and the what's the way that one thinks about it in kind of this theory of, for example, quantum electrodynamics, the quantum theory of electromagnetic processes, is that there are virtual photons being exchanged. So photons are the particles associated with electromagnetism. When you have a beam of light or something like that, you can think of it as light waves, but you can also think of it as a stream of photons, a stream of particles of light. And normally when you have just a light beam or something where it goes a long distance, you've just got photons that are happily moving through the vacuum or whatever, moving through, and they're just, the photon exists and keeps going, so to speak. But there's another way that photons can work, which is they can be emitted by, let's say, one electron and then absorbed by another electron. And that can happen in a very short time. One electron emits a photon, and then pretty soon that same photon is absorbed by another electron. And when the photon is emitted, if it can kind of give a certain, the photon can carry momentum. So you've got these two electrons, they're just going along, they're not emitting any photons, they just go in straight lines. But if those electrons if the momentum of one of those electrons is transferred through a photon to the other electron, that transfer momentum will kind of kick the other photon in a certain direction. And so you can think of the electrical force of attraction as being through the exchange of a series of photons between these electrons. And so what's happening is that there's this sort of exchange of momentum, which is kind of transferring force from one electron to the other and causing it to have, let's say, a force of attraction between the electrons or a force of repulsion between the electrons. That will be the immediate thing for electrons which are both negatively charged, two electrons both negatively charged. There's sort of a photon emitted from one and it kicks the other one away. And that's sort of the force of repulsion. And this is happening between two electrons that are nearby. You have all these photons being emitted and absorbed, and that's happening all the time. And that's a way of understanding what causes electrical forces. Well, there's one tricky thing here, which is those photons are not the same kinds of photons quite as the photons that you would have kind of in a beam of light. In a beam of light, photon starts off, it just keeps going forever. In these photons that are being emitted and reabsorbed, the photon only kind of exists for a limited time. And the way quantum mechanics works, the uncertainty principle implies that when a photon exists only for a very short time, the standard sort of properties of a photon don't need to be there. So an ordinary photon is a zero mass object. It goes at the speed of light, it has zero mass, etc. When these photons are being emitted and reabsorbed, because they exist only for a very short time, they don't have to act like zero mass things. They can act like non-zero mass things just for that very short time. The longer the time, the closer they have to be to zero mass. And in the language of particle physics, they're usually referred to as being off their mass shell. And the reason it's called that is because you imagine that the momentum of this may be more technical, but you imagine that momentum is a vector, and that vector can be kind of the length of that vector defines length of the momentum 4 vector, which is a combination of energy and ordinary momentum. The length of that defines the effective mass of the object. And so that length, when you have these, there's a sort of a shell of vectors which are all the same length. And if the thing isn't, if it isn't at that length, then it doesn't have the effective mass of the thing is not its normal mass. So anyway, these so-called virtual photons, these photons which exist only for a very short time, those are the things which are the what's really exchanged when there's electromagnetic force acting from one object to another. Okay, so that's how it works for electromagnetism. So a chap called Hideki Yukawa back in the 1930s had this idea that maybe strong nuclear forces were associated with the exchange of another kind of particle. And that particle became called the pion, and or earlier the pi meson, but nowadays the pion. And the pion is a particle that is, well, it is, again, it's something where a proton is going along and it can emit a virtual pion, which is then absorbed by another proton. And that exchange of the virtual pion can lead to a force from one proton to another. It happens to be always an attractive force in the case of pions. And the pion, unlike a photon, is not zero mass. It has a mass of about 1/10 the mass of a proton. And the fact that it doesn't have zero mass means that when you separate protons further away, it's not obvious this will be the case, but this is just how the math works out, that the kind of force of attraction between protons has a piece that is just like in electromagnetism, 1/r², but has another piece, which is an exponential that's basically a version of the mass of the pion multiplied by the distance. So it's e to the minus mu r over r is the typical formula. So a thing with 1/10 the mass of the proton has a sort of effective distance associated with it that's on the order of 10. I don't know. It's a distance comparable to the size of a proton, comparable to the size of an atomic nucleus. And so what happens is, at these very short distances, there's lots of pions being exchanged, But as you pull the protons further away, the pions, they're because of, for reasons that are, I mean, they're easy to explain mathematically. The number of pions that kind of can be exchanged goes down very rapidly. And so that means that there isn't a force of attraction between protons that are far away, but if you make them go close together, then there's this big force of attraction that comes from the exchange of lots of these virtual pions. There's virtual photons being exchanged between protons that are pushing the protons away. There's virtual pions being exchanged that are pulling the protons together. So in any case, this beyond protons, there were and neutrons, pions were discovered as these things that are part of the strong nuclear force. Now, I should explain something. The things get more complicated. There aren't just pions. There are a whole collection of these so-called meson particles, which are sort of available to be exchanged between things like protons. So, for example, there's a thing called the rho meson, F meson, a whole series, a whole zoo of these kinds of things were discovered mostly in the 1960s. One feature of these things is, and this is again a sort of a tricky thing of quantum field theory, these different particles are characterized by having a certain mass. They're also characterized as having a certain spin. Roughly, that is, you can think of them as little tops that are spinning around, except that in the case of an electron, you might think it's a zero-size top, but yet it still has an angular momentum. It still has some sense in which it has a kind of a rotary, it's not really a motion, but it's some rotary characteristic, so to speak, that's usually called spin. We can talk about quite separately, that's a whole separate discussion, what spin really is. We're beginning to really understand that in our physics project, actually. But anyway, all particles are characterized by having a certain spin. So for example, electrons have spin 1/2. Protons have spin 1/2. This is that's a thing. Photons have spin 1. Pions have spin 0. Gravitons, the analog of photons and so on for gravity, have spin 2. And it turns out that these different spin numbers say a lot about the general properties of how a particle behaves. So for example, particles with half-integer spins, so-called fermion particles, have the property that they obey this thing called the exclusion principle that says if you try and stuff lots of these particles in the same place at the same time, that won't work. You can't do that. If you have particles with integer spin, so-called bosons, of which photons are example, pions are examples. If you try and stuff lots of photons in the same place at the same time, they'll happily hang out together. But fermions exclude each other, don't do that. Another difference between particles of different spins is when you're exchanging particles, like you can, well, that characteristic of whether you can just sort of have a particle going along and just sort of create another particle that it can exchange with another one is something where you usually are exchanging integer spin particles between, well, particles of either integer or half-integer spin. And so, for example, in the case of electrons, you've got these electrons going along, they have half-integer spin, they're exchanging spin 1 photons, and it works out that you can do that. You can kind of have a spin 1/2 particle, it emits a spin 1 particle, it can happily sort of keep its identity as a spin 1/2 particle. If it was trying to exchange a spin 1/2 particle, and there are theories in which that is how things work, but if it was trying to exchange a spin 1/2 particle, it couldn't stay as a spin 1/2 particle itself. Okay, so another characteristic of these different particles that are exchanged, spin 1 particles, photons, have the property, spin 1 particles like photons have the property that when the charges of the things are the same, then there will be a force of repulsion. When the charges are opposite, there'll be a force of attraction. That's true when a spin 1 particle is being exchanged. When a spin 2 particle is being exchanged, it is the case that it's always an attractive force. And it's because gravitons, you can think of gravitons as being spin 2 particles. That's why gravity is, so far as we can tell, always an attractive force. There's no anti-gravity. There's no negative mass things, at least, well, There might be negative mass things. That's a question about cosmology. That's a separate problem. But in sort of the normal situation, there aren't negative mass objects. All objects have positive mass. All objects feel an attractive force of gravity. And you can interpret that as being associated with the fact that gravitons are spin 2 particles. So pions being spin 0, the even spinned particles have this feature that they're always attractive. Odd spin particles have the feature that they lead to repulsion with like charges and attraction with opposite charges. So pions are always produce an attractive force because they're spin 0. So they'll always pull protons together, pull protons and neutrons together, etc. Okay, but in the zoo of particles, there is a particle called the rho meson that is a spin 1 particle, and it produces a force of repulsion between protons. Then the F meson is a spin 2 particle. It produces a force of attraction between protons again. There's a whole zoo of these things. And the way it works is that a pion has the range of the sort of force associated with pion exchange is a certain size. Because pions have a mass, they have a mass of 135 MeV, which is a proton has a mass of 938 MeV. So it's the pion is a mass about 1/10 the mass of the proton. A rho meson has a mass of 770 MeV, something much closer to the mass of a proton. And because it has a higher mass, the range of its the range over which it can sort of exert a force, the range of its the range that it has is smaller. And so what you see then is at very long distances, protons just don't notice that they're there. When you get within the range of pion exchange, you'll have a force of attraction between protons. When you push the protons even closer together, you'll get within the range of rho meson exchange, and the protons will repel each other again. Potentially, when you push even harder, you get them even closer, you get within the range of F meson exchange, and they'll sort of attract again a bit more. Actually, people thought in the early 1980s, people wondered whether there might be a different state of matter that you could get to by just squashing it really, really hard and having it be kind of not the nucleus not be bound together by pion exchange, but have something like F meson exchange or something be the thing that would sort of crush it into a super dense nucleus that would be of a different kind than ordinary nuclei. No such thing was ever found. It probably isn't possible, but that was sort of a consequence of this idea. Okay, well, all of this goes to say that there's a whole zoo of particles. There's all these particles like these mesons, which are associated with many of those are associated with nuclear forces. There are also many other kinds of particles that were discovered. This was as soon as particle accelerators got turned on in the 1950s, people started discovering new kinds of particles. So in addition to protons and neutrons, there were so-called hyperon particles discovered, which so-called strange particles. They have all kinds of names, the lambda particle, the sigma particles. I used to be a big enthusiast of these things when I was a kid. I could probably still remember the lambda particle has a mass of 1115 MeV, which is a bit heavier than the proton. Sigma particles, I think it's 1385. So there were all these different kinds of particles. Most of these particles you don't normally hear about because they're unstable. They have lifetimes of order a billionth of a second or less, a tenth of a billionth of a second, things like this. So for example, a lambda particle decays into a proton and a pion, or a neutron and a pion, decays in, I think 10 to the minus, 100 millionth of a second, I think. It decays that way. So you make a lambda particle in a particle accelerator, pretty soon it self-destructs and turns into protons and pions. By the way, pions are also unstable. Pions decay most often into, in about 10 to the minus 8 seconds, into, well, actually, there are 3 kinds of pions. Boy, particle physics is complicated. There are 3 kinds of pions. There are pi pluses, which have positive charge, pi minuses, which have negative charge, and pi zeros, which have 0 charge. and these different kinds of pions, they're all things which are exchanged inside atomic nuclei, but they have, if you have one of these pions, and you make it in a particle accelerator, it has a different fate. So pi 0 decays rather quickly, 10 to the minus 16 seconds, into 2 photons almost all the time. And the pi plus and pi minus decay into most often into a muon and an antineutrino. Muons are particles that are very much like protons, except 206 times heavier, and muons decay in about 2.2 microseconds into electrons and a neutrino and an antineutrino. Pions are when you have cosmic rays that are radiation from the sun that hits the atmosphere of the Earth, most of what survives at sea level is muons. And you get, there's a muon going through you, once, let's see, it depends how big you are, but roughly a few times a minute, a muon will go through you. And you can, so anyway, there's muons are a different kind of thing. They're particles like electrons, so-called lepton particles. The particles that are subject to electromagnetic forces, but not subject to the strong nuclear force. Particles that are subject to the strong nuclear force, usually called hadrons. That's things like protons, neutrons, lambda particles, pions, all sorts of other kinds of things. There's a whole zoo of particles. Could talk about them. I consider many of these particles my personal friends, so to speak, and could tell you in probably great detail about each of these things. But in any case, around the proton, there are a lot of other sort of proton-like particles, usually called baryons. And in addition to proton, neutron, lambda particles, sigma particles, there are things called psi particles, the cascade particles, because they decay first to a hyperon, like a sigma or lambda, and then to a proton. And then, so a whole zoo of these particles discovered. And then that was on the sort of proton-like particles. Then there is a whole zoo of pion-like particles, so-called kaons, which are the eta particle, just a whole zoo of these things. The mesons tend to have masses that are, at least the simplest ones have masses that are maybe half, maybe a tenth of the mass of a proton, whereas the baryons, the proton-like particles, have masses a bit more than the mass of a proton. Okay, so there's this whole zoo of particles, and by the 1960s there were hundreds of these things, and it's like, how does one understand what these are? And so that led to this idea of the quark model, and it was sort of a thing a bit similar to what people like Dalton and Mendeleev and so on had done in thinking about chemistry and chemical elements and so on. It was kind of a thing where you could notice that, oh, this particle combined with this particle and did this and this reaction. And so you could start to guess, how could you think about what reactions were possible and what were not possible? So, for example, a big thing that was discovered in the 1950s was the so-called associated production of strange particles. So protons, neutrons, these are non-strange particles. They're everyday kinds of particles. Pions, also non-strange particles. But there were these other particles, the lambdas, the sigmas. These were so-called strange particles. And then on the sort of pion side, there were things called kaons, which were considered strange particles. And what was discovered was that in a standard sort of particle accelerator that was colliding protons together or whatever else, you would get strange particles always produced in pairs. There would always be, you would never get a single strange particle produced. You always get a kaon and a lambda particle, or a sigma and a whatever else. So that was an observation, and that was sort of one clue about how things worked. Well, the thing that kind of got realized in around 1960 was that you could think about these particles as being sort of, you could account for what reactions could happen and what reactions couldn't happen by thinking that all these particles were made of some underlying more fundamental particles that Murray Gell-Mann called quarks. Q-U-A-R-K. So the idea was a proton would have 3 quarks. Okay, first point, there are 3 kinds of quarks. At least that was what was thought at the time. What became known, they weren't originally called this, but what became known as up quarks, U's, down quarks, D's, and strange quarks, S's. And so the idea was a proton contained an up and up and a down. A neutron contained an up, a down, and a down. A lambda particle would contain an up, a down, and a strange particle, a strange quark. Now, one of the things that's tricky is, okay, if a proton contains an up and up and a down, proton has an electric charge of +1 unit. And a neutron, let's say, contains an up, a down, and a down, has an electric charge of 0. A lambda, up, down, strange, has an electric charge of 0. A sigma plus, for example, is a up, up, strange, and it has an electric charge of +1. And so you can try and figure out from all these things, what does that mean the electric charges of the quarks are? And so what you can figure out from that is it means an up quark has an electric charge of +2/3, a down quark -1/3, and a strange quark -1/3. People at first thought that was incredibly shocking, because what had been discovered, to everybody's great surprise, is that electrons have exactly -1 unit of electric charge, protons exactly +1 unit of electric charge. And it seemed to be the case that electric charge was quantized in units of 1 electron charge. Electron would be -1 unit, proton +1 unit, etc. But that everything was an integer number of units of electron charge. And so when this idea of quarks came up that had non-integer charges, 1/3 integer charges, +2/3, -1/3, and so on, that seemed like a big shocker, because among other things, nothing had ever been observed that didn't have integer charge, integer amounts of electric charge. So that was sort of the first shocker, was, oh, these are non-integer charges. Now, one of the things that came up was you could look at all the possible combinations of up quarks and down quarks and strange quarks and so on, and you could predict what particles should exist, because the idea would be every possible combination of quarks would make a particle. And so in particular, strange, which, because strange quarks have strange quarks have charge -1/3, so strange is a particle with a total charge of -1, it also has a strangeness quantity of 3, because it has 3 strange quarks in it. So that particle was predicted from the quark model that particle would exist. Well, it hadn't been seen so far. So in 1965-ish, I think, that particle was discovered. And it was discovered, actually, even its mass had been more or less predicted from working out each of the quarks roughly has some definite mass. And so the mass of a particle made from, let's say, 3 quarks is roughly the sum of the masses of the quarks. It doesn't quite work out that way, and I'll explain why later. But so the big excitement was that this strange particle was discovered. It was named the omega minus. And that was kind of a very strong validation that this idea that particles were made of quarks was right. Okay, I should explain also the mesons are also made of quarks, like a pion is also made of quarks. But whereas the baryons, the proton-like things, are made of 3 quarks together, the mesons are made of quark-antiquark pairs. So, for example, a pi plus is an up-down, up-anti-down pair. So it's an up quark combined with an anti-down quark. So antiparticles are always the opposite charge version of a particle. So for example, for an electron, which has charge -1, there's a positron, which has charge +1, which is the antiparticle of the electron. And for example, if you create, you can create from a photon, actually, you can create an electron-positron pair, both the electron and its antiparticle, the positron. If you just have an electron and a positron hanging out and they get close to each other, they'll eventually, because they're oppositely electrically charged, they'll attract each other, they'll kind of spiral in, and eventually they'll sort of crash into each other. And when they more or less when they crash into each other, they annihilate, and the mass of the electrons are converted to energy, and that and what you get typically when electron and positron annihilate, you get two photons produced. And that's the typical thing. If you take a particle and its antiparticle, a proton, antiproton, they can annihilate, and what gets left over is a whole bunch of other particles. So for example, proton, antiproton, you could, if you did it very, very, very carefully, you might get two photons out. More often, you'll get a ton of pions and things like that out. Okay, so these pion-like particles, the mesons, quark-antiquark pairs, the baryons, the proton-like particles, quark-quark-quark combinations. You might wonder, are there other kinds of particles that are like 5 quarks and different combinations of this? And there've been slowly people have started to observe those kinds of things. But mostly it's quark-quark-quark or quark-antiquark are the most common kinds of particles that you see. Okay, so boy, all this stuff, it's taking me much longer to explain this than I thought it might. I think it's because I learned about this stuff when I was a tween or something. It all seems very obvious to me, and almost anyway. But to continue, so we're back to talking. So we have these quarks, and we found that protons are made of 3 quarks, pions are made of quark-antiquarks, and so on. Okay, so then I had mentioned when people were actually trying to figure out, probe sort of microscopically what's inside a proton by shooting electrons at it, that what had been discovered was that most of the time the electrons just go straight through, but occasionally they get scattered at a big angle, suggesting that there's sort of a hard bit inside the electron. So a big question for the early 1970s, early to mid 1970s was, there's this quark model that says, oh, a proton is made of 3 quarks, and there's this observation of, well, there's hard bits inside a proton, and those must be, what are those? And they were initially called partons, and there were quarks and there were partons, and were quarks and partons the same thing? Okay, the big sort of realization of the early 1970s was quarks and partons are the same thing. When we have scattering from a hard bit inside a proton, that hard bit is one of these quarks. Okay, well, the next question is, okay, well, if you hit that quark hard enough, why doesn't it come out? Why don't you manage to just sort of eject the quark from the proton? So this was a big mystery. It was kind of like, and then the question was, we know that in a nucleus, the protons are held together by the exchange of pions. The question is, what holds the quarks together inside a proton? So that led to this theory called QCD, quantum chromodynamics. And actually that theory originated from another observation. Right, so I mentioned this exclusion principle that says that 2 spin-1/2 particles, for example, they don't like to be in the same place at the same time. Well, quarks are spin-1/2 particles. And so in a proton, you would have something like an up and up and a down. And the problem was that people couldn't understand, how could there be 2 up quarks there that were sort of in the same state, same time, and why didn't they refuse to be in the same place at the same time? And so what then got realized was, well, maybe that's because the 2 up quarks aren't really the same. Really, they have some property that differs between those up quarks. And that property became called color. And the idea was that these quarks would have sort of 3 possible colors. And so when you have an up and up and a down, they're not really 2 identical up quarks. One's a green one and one's a blue one or something. That the term color has nothing to do with the color that we observe from in light and things like this. It's just a labeling of these different sort of characteristics of these quarks. So, okay, so that meant that there was this other kind of charge, different from electrical charge. It was a color charge. Okay, so then the idea was, well, maybe just like there's electromagnetism, which is associated with exchange of photons that are between particles that are charged with ordinary electric charge, maybe with this color charge, there was a sort of similar thing going on. Maybe color charge, there's another kind of force associated with that, associated with the exchange of other kinds of particles. And so this other kind of particle got called gluons. And the idea is that just as electrically charged things exchange photons, color charged things exchange gluons. Okay, so gluons, the idea was gluons, like photons, are massless particles. Okay, that's a little bit weird because we don't observe gluons, just like we don't observe quarks. You hit a proton as hard as you want, and so far as we can tell, it never disgorges its quarks. The quarks always stay confined inside. And so that was sort of a big mystery. It's the mystery of quark confinement, or sometimes color confinement. Why can't you have these color particles? Now, I should explain that in one feature of a proton-like particle, because there were supposed to be 3 colors of quarks, when you end up with you'd end up with a proton which had the 3 colors of quarks, all different colors, and so the overall proton would be sort of, in some sense, white. It would be a combination of all the colors. It would no longer have sort of obvious color charge. Same with a quark-antiquark pair. These were the sort of 2 combinations. If you have 3 colors, the 2 combinations are either the 3 colors, each different red, green, blue colors, or a red and an anti-red. Those are 2 ways to get an overall colorless object. Sort of explain why you would see the 3 quark case and the quark-antiquark case. So, okay, but then this idea of gluon exchange associated with color charge, that became the theory of quantum chromodynamics, QCD, the theory of quantum color dynamics, so to speak. And here's the sort of the big difference between what happens with electromagnetism and what happens with QCD. The big difference is electrons are charged particles. Photons do not have charge. Photons have no electric charge, so that means an electron is going along. It emits a photon. The electron keeps the same charge that it had before. Gluons, on the other hand, have color charge, and so a red up quark going along emits, well, something like an anti-red green gluon. Gluons have sort of these paired color charges, and then that red up quark turns into a green up quark. So the gluons, the way their color charges work is a little different than the color charges of the quarks. They're like paired color charges which basically say if a red quark emitted this thing and turned into a green quark, then that means that the gluon it emitted is an anti-red green gluon. In the way this was originally understood was using group theory and the theory of the group SU3, and so the whole lot of story about the representations of the group SU3 and how that related to quarks and gluons, but that's not really relevant to what we're talking about here. The thing I just described is a perfectly adequate description of what's going on there. So that means these gluons have color charge. So that means gluons exchange gluons with gluons because they can emit gluons. They have a color charge. They can emit gluons. They do. So gluons exchange gluons with gluons. Okay, so what? Well, in the terminology of these things, that means this is a so-called non-abelian theory. That word abelian comes from theory of groups. That it just is basically saying the things that exchange, the things that are exchanged are themselves capable of exchanging things. Okay, so what? Well, the big thing that had to be explained was why do you not get free quarks? Why can you not pull things apart with the quarks being arbitrarily far away? Why do these gluons keep pulling them in and do so increasingly strongly as the quarks are pulled apart? Okay, so another big thing was discovered in 1973 is a phenomenon called asymptotic freedom. And that phenomenon, oh boy, this is a little complicated. Okay, I hope you guys have been following this. I'm sorry, particle physics is more complicated than I remembered. But I think it sort of often takes a whole graduate class to explain all this stuff. So maybe we're coming out ahead here. Let's see. The thing that I was going to explain asymptotic freedom. So the big question is, when you are exchanging photons, for example, between electrons, what's the rate at which photons are produced? And that's determined by a constant in the theory of electromagnetism. It's a constant called the fine structure constant, usually denoted alpha. And it turns out it happens to have no units, so it's approximately equal to 1/137. So that characterizes kind of the rate at which photons are produced by an electron, and that determines the amount of force between electrons produced by electromagnetism. So the fine structure constant is what's called the coupling constant of quantum electrodynamics, the thing that determines the rate of photon production, the effective force between the electrons. All right, so there is a corresponding coupling constant for QCD, which is the thing that determines sort of the rate of gluon production by a quark, the effective kind of strength of interaction between these quarks. Okay, here's where things get a bit tricky. So around what happens is, depending on kind of depending on the amount of momentum that is going to be transferred between particles, the effective coupling constant is different. Why on earth is this true? The reason is basically this, that, okay, you've got an electron going along, you think of it as just, oh, it's an electron, it's just going along, it's happily doing its thing, but actually it's constantly emitting photons, virtual photons. It's actually more than that. It's emitting virtual photons that turn into virtual electron-positron pairs. And there's a whole cloud of stuff going on around you. Just think of it as an electron, but according to quantum mechanics, there's this whole sort of cloud of other stuff that's happening around the electron. And that cloud of other stuff is around an electron, not such a, it's a pretty dilute kind of cloud of stuff, but there's always this, virtual electron-positron pairs, virtual photons, a lot of other random stuff going on around this electron. The same is true around a quark. But around a quark, there's all these gluons, virtual gluons, there's virtual quark-anti-quark pairs, all kinds of things like this. Okay, that means that around every quark, for example, there's this kind of coating of other stuff. And one feature of that coating of other stuff, all these virtual gluons that are being produced, these gluons have color charge. And that means that a gluon, you have a red quark, for example, and it's around it, it has this kind of big coating of other gluons with, anti-red green, blue anti-red, all sorts of different combinations of colors that are in the kind of the cloud around this quark. Okay, now the thing is that you thought there was a red quark there, but actually there's all these things with different color charges that are sort of in this cloud around it. So if you look at this cloud from a distance, what you mostly just see is all of these things with all these different color charges, and they're all plus version of a color charge or minus version of a color charge. What happens is that the color charge of that little red quark in the middle is screened by the color charges of this sort of random cloud of gluons around it. So that means that at a large distance, it will seem like that red quark in the middle really doesn't, you can't even tell that it was a red quark in the middle. It's covered by these things that have, actually, this explanation is not going in quite the direction it should. Let me give this version of the explanation for an electron first, because there's a little other thing that happens in the case of color charge. In the case of an electron, you have the electron is there, you've got these electron-positron pairs, the electron charge -1, positrons in the electron-positron pairs charge +1. Eventually, there's a sort of cloud of electrons and positrons around the electron, which in some sense will screen the charge of the electron, roughly. This is not as simple to explain as I might like. Roughly what happens is, if you send in a very high energy particle to go and sort of interact with the electron, it's essentially probing very small distances around the electron, and it will effectively see the naked charge of the electron. If you have a lower energy particle, and again, one of the pieces of intuition here is that according to quantum mechanics, the effective, we've talked about the sizes of particles as sort of the actual size of the particle, but in quantum mechanics, the position of a particle gets smeared out over a certain region. That's why, for example, when you look at light, you can think of it either as photons, which are like single particles of light, or waves, where there's sort of this whole smearing out of where the photon is. And that smearing out process, the higher the energy, the shorter the range of that smearing out. So effectively, the higher the energy, the more precise a positional probe something can be. So the higher the energy of a particle, the smaller the effective distance that particle can sample. And so sort of the intuition is when you send in a high energy particle to probe some other particle, the higher the energy, the smaller the range, the smaller the more powerful the microscope you have, and the smaller the range that you're probing. So when you have a high energy particle, it's like you're drilling into the inside of this kind of cloud of stuff, let's say around an electron, and you're seeing what the raw electron is like. When you have a low energy particle, you're seeing this much more screened version of things, which and the point then is that the charge that you see is larger if you're seeing sort of into the core of the thing than if you're seeing this kind of whole cloud of shielding of other virtual particles around it. So that means that leads in the language of particle physics, that's sometimes called a running coupling constant, or an effective coupling constant, where instead of it being that 1 over 137, it's a number that is for example, when you probe right into the sort of further in, the 1 over 137 actually gets bigger, and you kind of are seeing something which is a larger effective charge, larger effective coupling constant, larger effective. It's again complicated. It's the sort of larger effective effect of the charge, so to speak. Okay, so the big thing that was discovered for QCD was that when you kind of probe in to sort of smaller and smaller distances, you actually see a lower effective coupling constant. The thing I was explaining before, I should have been talking about the fact that these gluons are just adding more charge, and quite how you can argue that is not completely obvious, but instead of it shielding the charge, it's sort of adding more charge as you go out in this cloud. And so if you can probe into the center, you're seeing in effect lower charge, and that means that when you kind of the effective force between quarks, for example, associated with gluon exchange, if you look at it at very short distances or very high energies, it's a much lower force than if you look at it at larger distances. And so that phenomenon of asymptotic freedom, that when you go to very high energies, the effective force of attraction between quarks is lower, that was an important thing that was observed experimentally to be the case, and that was kind of a big piece of evidence for QCD. Okay, so at very short distances, the forces become smaller. At larger distances, the forces become larger. How does this work? It's actually not too difficult to see intuitively how it might work. So you exchange, you have an electron, for example, it's a charged particle, it's producing photons. If you just have that little electron in the middle, you can think of it as just producing photons streaming out in all directions. And in fact, the inverse square law of attraction is really just because you produce a certain number of photons, they're going out in all different directions, but the density of photons at any given place that you're sampling goes down like the area of the shell, the area of the sphere around the photons. So if the sphere is as radius r, the area of the surface of the sphere is 4 pi r squared, and that means that the the density of photons, if you have a certain number of photons streaming out from the electron in the middle, the density of photons goes down like 1 over r squared, and that's what leads to the 1 over r squared force law for electromagnetism. Okay, so with photons, they don't interact with each other. They don't have charge. They just are separately streaming out in all directions. With gluons, that's not the case. Gluons have color charge. So these gluons, they want to be streaming out all directions, but actually they don't get to do that because the gluons interact with each other. And so instead of forming this thing that like sort of the idealized hedgehog with the things going out and the spines going out in all directions, instead of that, the gluons are pulling on each other and pulling each other together to make these kind of these whole strings of gluons where you've kind of pulled things together. You pulled all these gluons together. They don't go out in all directions. They just go out in this kind of like umbilical cord between, let's say, one quark and another quark. And so roughly what happens is the reason that there is that means that as you pull the quarks apart, instead of the force of attraction going down because there are fewer gluons that get from one quark to the other, that isn't the case at all. Instead, you've got this tube of flux of color flux, basically, that are connecting these two quarks. And the harder you pull, the further you pull, the sort of the more tension there is in this tube of color flux. Actually, what happens is when the tension in the tube of color flux gets too high, it breaks. But what happens when it breaks? Well, it actually forms mesons when it breaks because the two ends of this flux tube essentially become the sort of one end. If you have a quark at one end, it'll end up with making a quark-antiquark pair, and one side of the flux tube will get another quark, the other side will get the antiquark, and that the sort of pieces of flux tube will then just end up as mesons. So essentially, when you pull it hard enough, it's like breakdown in this QCD vacuum, more or less. It's like you end up eventually just producing more particle-antiparticle pairs. So anyway, people have been trying to figure out, is this really the right picture? Is this the whole story? Is it really the case that there's no way you can separate these quarks and ever get them to infinity without them having these sort of umbilical cords connecting them to other things? How does that work? And it's been a long-running story, whether it's possible to actually prove confinement of quarks. It's never been proved. There are really good arguments for it. I actually kind of suspect that some of the things that have come out in our physics project will give one a new way to think about how to prove these things. But it's what one can do is one can simulate on a computer instead of taking quarks to be sort of in any position, you can say they're on a lattice, and you can kind of simulate kind of these idealized kind of lumps of color energy or something, like sort of discretized versions of gluons, and you can try to work out sort of what the typical possible configurations are. Now, the way people do it, which I think is kind of crazy, but that's the way it's been being done for a long time. It's the standard formalism of quantum field theory. You're really just looking at what are the possible configurations of quarks and gluons. You're not looking at the time evolution. You're not looking at, oh, if you pull these quarks apart, this is what's going to happen. You're just saying that you're looking at these are the possible configurations that can exist at a certain time. For technical reasons, there is a real hack that's done that treats time as like the various directions of space. It's kind of Euclidean space-time, where which has a lot of weird features. But that's what's done for technical reasons when people do so-called lattice gauge theory simulations. And what has happened is there is, again, reasonable evidence that in this kind of somewhat distorted version of what QCD is like, put on a lattice, that you look at certain kinds of, you just look at certain kinds of correlations between different, between sort of what's happening in the color field, for example, at different places on this lattice. You can get sort of another kind of piece of evidence that, yes, it does seem to be the case that as you sort of move things further apart, it behaves like this kind of like this flux tube picture, and that it will show confinement. But it's never been proved that that really is always the case. people have looked for sort of free quarks, and you know, you might ask the question, if you've got a 1/3 charged particle and it's kind of hanging out in seawater or something, where would it go? And you know, it makes these weird atoms that have non-negative charge, and they have a lot of weird properties. And there are effectively experiments that have been done that look for this and haven't found anything. But the sort of the general problem of confinement of quarks has never really been solved. One of the things that is tricky is when you have this color charge and so on, and you have these gluon fields, and the gluons are all going around and so on, how organized are these gluons? Are they all just streaming out in a nice sort of hedgehog, you know, idealized hedgehog pattern, or are they making these complicated swirls like in a turbulent fluid? My strong guess is that they're making complicated swirls, and actually some properties of the statistics of lattice gauge theories suggest that there is something analogous to turbulence that's happening in those kinds of systems, and that it's possible that in the end, the story of quark confinement will be closely related to stories about turbulence in fluids, and to one of my favorite topics of computational irreducibility and so on. But in any case, that's boy, that was a long answer. Sorry, guys, that was but I did cover a pretty good swath of particle physics and quantum field theory there. I could, as I say, that's probably at least at the qualitative level, that's a decent chunk of some graduate class in those kinds of things. So maybe I wasn't doing too badly here. But as I say, because I learned all this stuff when I was quite young, it all is like, oh, of course it has to work that way. And I'm not sure I've ever explained this stuff before. Maybe I've talked about some pieces of this. Okay, there's just one or two questions here that follow on from what I was talking about, just so I can cover those. Mustafa asked, how do we discover the strong nuclear force? I think I more or less covered that. I mean, it was really a hypothesis of this person, Hideki Yukawa, that there would be these particles that would be the things that bind protons together. And what was a little bit confusing was cosmic ray experiments discovered muons before they discovered pions. And people assumed the muon must be the pion, must be the thing that Yukawa had suggested would exist, but it didn't have the right properties. But a few years later, pions were discovered, and all was well. Let's see. Zayden asks, is there a finite number of subatomic particles, or will we always find new ones? Okay, there are not a finite number of subatomic particles. What happens is, okay, in a hydrogen atom, for example, there are, there's the proton in the middle, there's electrons in the hydrogen atom. There are different possible energy levels of the electron. And the different energy levels of the electron are, when you solve the equations of quantum mechanics, the Schrodinger equation in this case, you find out that there are different normal modes. It's kind of like you have a string, and you can bow the string and it'll bow out once, so you can bow it so it bows out twice when you're attaching it at the two ends, or 3 times or 4 times, and any integer number of times. You can have any mode of the string, at least in principle, if you have a flexible enough string. So in a hydrogen atom, same thing is true. There are these different modes of how the electron, the sort of configuration of the electron. In the equations, it works very similar to how it works for strings. It turns out for a hydrogen atom, the energies of those modes, it's like 1/n². They get closer and closer together, and eventually at 13.6 electron volts, if you put that much energy into a hydrogen atom, the electron will escape. But up to that point, you're getting more and more and more and more and more energy levels of the electron in the hydrogen atom. But it so happens there's a limit, and eventually the hydrogen is ionized, the electron escapes. Okay, for quarks and antiquarks, for example, same story. You get these modes of the quark and antiquark. They can be in these different excited states, and they're a discrete integer collection of these. But unlike in the case of the hydrogen atom, where eventually the electron escapes, the quark and antiquark, however much energy you put in, they'll never escape. they'll just wobble around in different ways. And so, for example, the pion is the lowest excitation level of a, let's say, up-out anti-down quark. The rho meson is the next excited state. It's also made from an up and an anti-down quark, and at least the positive rho meson is the rho plus. But it is an excited state of the pion, an excited state of the quarks in the pion. The F meson is another excited state, and you just keep going. And these excited states, roughly, the mass of the progressive excited states, roughly, well, let's see, the square of the mass is on a linear, so that it goes up like the square root, roughly, of the excitation level. So yes, you can keep going forever. You can keep going with more and more and more excited states. Why aren't they as exciting as they might be? Well, the reason is the higher the excited state, the faster it will decay. So, for example, as soon as you get past the first few, they're all decaying in like 10 to the minus 24 seconds, a trillionth of a second, which is kind of a short time. So they're not as, you don't, that's why they're sort of less important in some sense. Now, but it is the case, so that these energy levels for the baryons, for the proton-like particles, they're more sort of evenly spaced levels rather than square root type thing. They're evenly spaced levels that just you keep on putting in more energy, and it's like it never ionizes because the quarks never escape, and you just get more and more excited states, more and more different kinds of particles. So, for example, the proton's excited state is basically the delta particle, and then you have they just get named by their masses, and they sometimes have stars. I don't know if there's a delta star particle. When I knew about these things, I learnt what all these particles were, but I learnt that in 1973 or something. And there are a few more particles that have been discovered and a few different names that have been given to them. But in any case, the thing that the question is, in the quark model, you just get these particles, different kinds of particles that are kind of like evenly spaced, different excitation levels. There was an earlier theory, so-called Hagedorn theory, which said that maybe the particles, there would be just more and more and more different kinds of particles. You increase the energy, you just get a higher and higher density of states of particles. And one feature of that theory is that if that's the case, there's actually a maximum temperature that you can get for anything, because instead of, as you put more energy into a system, normally that would raise the temperature by having the things in the system, molecules or particles or whatever, run around more quickly, leading to a higher temperature. But if you have more and more and more different kinds of particles, instead of the energy going into the kinetic energy of particles running around, it goes into making newer and newer different kinds of particles. But that theory turned out not to be correct. So yeah, so there are an infinite number of particles, but they are sort of evenly spaced energy levels and so on, roughly. Nata is asking, how do detectors sense the presence of these particles? Okay, so for many of these particles, they are charged particles, and there are different kinds of detectors. So a very common kind of, an early kind of detector, like a Geiger counter, works this way. When you put a strong electric field across a gas, then if you put a strong enough electric field, the gas will break down. It's kind of like, that's how a lightning strike works. There's a very big electric field in the Earth's atmosphere, and when it gets too big for the air, so to speak, the air breaks down, and you get this kind of bolt of lightning that is a sort of ionized. The atoms in the air get ionized, and there's a sort of electrical conducting path that's formed. Well, when you have a particle, one of these charged particles, one of these go through a sufficiently sort of super set up gas where you've got a big electric field in it, if that one particle comes through, the gas is right at the edge of breaking down. And when that one little particle goes through, it breaks down, and you get this big sort of bolt of, microscopic bolt of lightning, so to speak. That's one type of particle detector. There are a whole variety of other kinds of particle detectors that work by being sort of right on the edge of a big effect happening. So another one is so-called bubble chambers, where you are sort of making a fluid be almost boiling, but it isn't quite boiling. It's just ready to boil, and as soon as one of these little particles goes through, it just that just kicks it over the edge, and you get this trail of bubbles. That was how the omega minus was discovered. Actually, it was in a bubble chamber. Then there are different kinds of detectors. The modern form of detector is actually using semiconductors. And essentially what happens is the charged particle, when you have like a memory chip, it's storing that bit in some number of, I don't know, 100,000 electrons or something, are either there or not there. And when this extra charged particle goes through, it can sort of tip it over from being a 1 to a 0 or the other way around. And you're more or less detecting that phenomenon. That's a sort of modern semiconductor detector. But that's roughly how particle detectors work. There are a whole variety of different kinds there. There's the early one was a cloud chamber, a bubble chamber, then the so-called spark chambers, where you get these sparks that are very much like lightning strikes. There are Cherenkov detectors, which use a slightly different effect. And then these semiconductor detectors, which I think have become more common these days. All right, I think we should wrap up here. So thanks very much. And that was interesting, trying to communicate a whole bunch of particle physics in a short time. But thanks for joining me, and see you another time. Bye for now.